and to everyone for coming here today. We're going to be talking about how to build and program a reliable robot, and this will apply to EV3, Spike Prime, and the brand new Robot Inventor set that just came out. So this is just a little bit of background information on us. We competed in First LEGO League for 8 years. Most notably, we won the Champions Award at World Festival in 2018. And as you can tell, we've been doing this for a really long time from the list of things that we've done. And we're also the founders, and we run FLL tutorials, Prime lessons, and EV3 lessons. And currently we are the co-captains of FRC 8027.
And as Arvind mentioned earlier, we are going to be talking about reliability today. And you might be wondering, why focus on reliability? Firstly, reliability is a #1 challenge that teams face. Number two, robots often tend to work at home, but you do not get the same results when you go to a competition and run it on competition tables. Third, robots only complete the mission sometimes correctly. For example, you may have a low success rate for a single mission. And four, because of 1 to 3, teams get frustrated. We are going to be discussing all of these in the following slides. We are going to begin with building for reliability. The bottom line is that everyone should build a robot that you should build a robot that you understand, because then you will know it the best, and you can build it sturdy, and it should be easy to repair and easy to code. And if you build it, you will be able to do all of these things more easily.
The first step in making a reliable robot is building a strong and sturdy robot. This also goes for attachments that you build it as well. If they're strong and don't flop around, they're likely to be more reliable. Let's take a look at the examples in the images. First, let's take a look at the example in the top left with the axles. Which one do you think is going to be stronger? I would say that number 1 is going to be stronger because it is made up of multiple shorter axle segments, and this makes it less likely to twist as well as bend. Next, let's take a look at the lift arms in the bottom left. Which one do you think will be stronger? In this case, I would say that number 2 is going to be stronger because each lift arm has multiple connection points. It's connected on both sides, making it less likely to bend. Finally, let's take a look at the example on the right. In this case, we're going to have to look at which would be the most strong, as well as which would be the most efficient. Now, I would say that number 2 and 3 will be just as strong, but number 2 is more efficient because it uses fewer parts. You should always go with the most efficient option, but do not sacrifice strength where you need it. As you can see, the concept of using what's called cross-beaming is used in example 2, which is the idea of putting a lift arm or a piece that will prevent other parts from coming apart without that beam, which is what's in example 1. The 2 frames would be able to split apart, but that lift arm prevents them from splitting, and that's the idea of cross-beaming.
Next, we are going to talk about cables. And oftentimes teams will build the robot and then not wire it while building. So after you're done building the robot, you may notice, oh, wait, I don't have any space to put my wires. And if you just don't think about the wires as you're building, your cables can easily get in the way while changing attachments. And if you have your wires overhanging, they can mess up the robot's movement and get caught on other mission models, or even the wall. If you're using the Spike Prime or new robot inventor, we recommend using the cable clips that come in the set to easily tuck the thin flexible wires away. If you're using the EV3 wires, here are some examples. These can also work for the Spike Prime cables also. But if you look at this top one, it's using two lift arms and two of these blue pegs to essentially hold this wire in place between them. This second piece here is actually a gearbox just sealed off with one of these pieces and a stick. The wire is nicely held away using the gearbox. And you can actually see this in action in this attachment. The wire is nicely woven through the attachment and all the way across to where the brick would be. And this will prevent it from getting caught in any attachments or on any mission models. Also, on the same note, somewhat related to the wires, is you need to keep your access to your ports open. For example, you need to make sure you can be able to charge your robot. You either have to leave a hole open to replace the battery or to charge it. And that is this hole on the back of the battery if you're using an EV3. And also don't forget to leave the download port open because at competitions, you're not allowed to use Bluetooth. And of course, leave your wires for your motors and sensors. But note on the Spike Prime, the download port and the charging port is the same USB port, so you only have to leave one port open. And actually, on another note, you cannot just take out the battery and charge it separately. You have to have it plugged into a hub in order to charge the battery.
And everything Sanjay just said about the Spike Prime also applies to the robot inventor.
Yes.
Next, we want to talk about how you can build a robot that navigates reliably. There are three things that we recommend. The first is having an outer wall. An outer wall will help keep your wheels straight and not bow or bend out. And it also allows you to align on walls as well as ride walls. And we'll show examples of this in just a second. The second thing is to use color sensors. Color sensors can be used to line follow on lines that are on the field, as well as square up on those lines. And finally, I mentioned this in number one, but wall riding helps you stay straight, and that can be done not only having that outer wall, but also sometimes having riding wheels that are along the wall to help make the riding more smooth. Now let's look at how we can apply these techniques in action on an actual competition robot. This is an example of DroidBot C, and as you can see, it has an outer wall. An outer wall is basically a set of lift arms that go around all four sides of the robot. The lift arms on the front and back allow the robot to drive into walls and straighten out. The outer wall on the sides allow it to ride along walls. And if you notice in this build, we actually added wheels along the outer wall to actually allow it to ride along more smoothly. There's two color sensors that are separated from each other at opposite sides of the robot, and this is to make the squaring up on lines more reliable. And they're also far away from the drive wheels so that it makes the line following more reliable. You also notice we have a low center of gravity with the brick being low down. This will prevent jerking. And there's also level construction, which is important as well for weight balance. At this point, I would like to switch over to an overhead camera to discuss how these features can be applied to different designs. So this is an example for robots. the DroidBot C, this one is the one we just looked at. Now let's try and identify similar features in all of the other robots. Let's start with this one here. This is DroidBot E. And DroidBot E has that same outer wall that goes around the entire build that keeps the wheels sturdy and can be used for the same purposes as DroidBot C. Also notice that there's a low center of gravity to prevent jerking, and also a level construction. These two robots, this one is built using the Spike Prime, and this one using the new Robot Inventor set. These are attachments, but we'll talk about those in a second. There's a flat surface in the front and back to allow for lying on walls. To make this build as small as possible, which was the goal here, there is no outer wall, but it isn't too necessary in this case. These robots are also use very minimal parts and are connected very well in a sturdy way. Okay, let's get back to the presentation.
Okay.
So I kind of went over the next few slides live. Next thing that I want to talk about is some aspects that you have to consider when you are designing your robot. The first is height. So notice I was talking about how all the robots had a low center of gravity. Top-heavy robots tend to be very imbalanced, and when they drive quickly, they will jerk, which means they will, when they stop abruptly, they will tip forward or backwards. This is not something that you want, and so having a low center of gravity will be able to solve this issue and also allow you to travel at faster speeds, which will reduce time as you travel across the board. The next is the weight balance from left to right. So you need to make sure that the robot is symmetrical so that you don't have more weight to one side, which can cause the robot to not drive straight and swerve. Next thing to consider are the size of the wheels that you use. Large wheels are fast, but they are harder to control and tend to be less reliable than smaller wheels are. You should find a good balance between a large and a small wheel to maximize your speed and your reliability. Finally is the type of wheel that you use. Tires where the rubber is able to come off of the wheel or compresses easily tend to have a lot of variance and decrease the reliability of your robot. A personal example here is that Sanjay and I, when we were in Arkansas competing at the Razorback Invitational, one of our matches, the rubber actually had come off of the rim of the tire, and we didn't know that, and none of our missions worked because the robot didn't drive straight because it was off on one wheel. So that's something that you should make sure when you're choosing which wheel that you use.
After you build your robot, it is very important to test it. You need to test aspects such as, does your robot drive straight? Do the wheels slip? Can it follow a line well? Can it line on walls, etc.? We recommend creating a table similar to this one. This can actually be found on flltutorials.com. And after you fill in this table and identify the flaws, we recommend you modify the robot and test it again as needed. In fact, you can combine aspects of different robots that you have built. And if you have multiple EV3 or Spike Prime sets, we recommend building multiple at the same time. Be sure to document all the changes you make and all the robots you made. because this is all part of the engineering design process. Next, we're going to talk a little bit about some attachments. The first one we call an aligner. The way this works is we have these two bent lift arms on the edges, and then you can use this to go into, when you go into a mission model, you can actually straighten out your robot. So it actually allows you to have a little bit of a margin of error when going to complete a mission. Arvind, did you have some attachments that you could show us?
Yes, and I will show them right now. So these are the two robots I was showing earlier. This is an example of an attachment that comes on and off very easily. And it actually uses this gearing mechanism where the gears will mesh with each other when the attachment is placed on. And you notice that the axle here actually sticks out one past the gear. And this is to make, and this actually, the axle will go into this lift arm here. And so that makes sure that there's no slipping in the mechanism when it is on the robot. This robot has a very similar mechanism with the same gearing. The example in the slide was with this robot, which has a larger attachment that goes around the sides as well, and has the gearing on the bottom and an axle that goes into the attachment to make sure there's no slippage. This reduces time that you have to spend in launch area setting up your attachment because it comes on and on very quickly. Now, I know Sanjay was also talking about aligners, so I wanted to show an example of attachment that we created that uses aligners. So you can immediately notice here that there are two, I will try and move this out of the way. So there are two sets of angled pieces. This is a lot wider than the one Sanjay showed because the mission model that we were trying to align on was very large. And so there's an angled piece here, and then there's an angled piece on the other side. There was also a section here that we could align on. So we use these pieces on the left and right here to straighten up. And so there's several different pieces that you can use. If they have a curved shape, that's nice for aligning because it gradually will center the robot to the right location. Another thing that I wanted to show were some attachments. So Sanjay, did you want to talk a bit about passive attachments, and then I'll show an example?
Yeah, the next attachment that we want to show you is called a carabiner. Arvind, can you show that on the screen?
Yep. So this is
It's a carabiner, and if you have something that is hooped, for example, or a closed object, the way this works is it has a lift arm connected to a rubber band on the top. So it's eventually like a locking mechanism. When you push something in, it will become stuck inside of there until you remove it by hand. This is great if you have, as I was saying, a hoop or any closed object that you want to capture. Yep, just like Arvin is showing.
So this is just my example of something you'd want to grab, and it can come in but not go out. This version uses a rubber band, you can see, to make it want to go back, but there are some cases where you wouldn't need a rubber band. So for example, if this could just be gravity based, where it would go in and then gravity would make it want to come back if this was heavy enough on top. And so depending on the use, you might not need a rubber band. I think we have an example that doesn't use a rubber band in this attachment again. At the end here, there's the similar concept of something that can go in but can't come out. And this is just gravity based. This particular attachment also had an item in here that was dropped off as it picked up a hoop, which is interesting as well. While I'm showing this, there are other examples of passive attachments that you can create.
Yeah, one of them is a. Oh, okay, go ahead.
For example, this is a one-way curtain. A one-way curtain is used to collect items on the ground, and it's similar to the concept of the carabiner, where it can go one way, but not the other. Hence, it's called the one-way curtain. So if I had an object on the ground, it would be able to drive over and then pull it back with it, because these pieces are not able to go the other direction. And there's a few more here. There's some gravity-based attachments. Let's see if I can get a good angle of this. There's this piece up here, and the objective here was to deliver some kind of hoop to a location. So the piece would go onto this part here, and this was a passive attachment that was actually triggered by a motorized attachment. So as this gear rack went outwards, you notice how this dropped down, and so it would drop down and it would deliver something. So that's using gravity. On the right side here, we see a rubber band based attachment. So it wants to push outwards, and it was latched down by this piece here, so that when it pushed into the mission model, this would shoot outwards and activate something. I think I do have a few more. This is an example of pneumatics. And this is a pneumatic piston. I think you should be able to see that. Yeah, pneumatic piston. It's not hooked up right now, but there was a setup with pneumatic tubing and a pump and stuff like that. But the idea here was that we're translating the linear motion of the pneumatic piston into something that moves outwards. So as this pushed down, this pushed outwards, and it was used to activate submission by pushing it. Finally, there is one more example of rubber bands. And what this attachment did is there's these pieces at the bottom, and when it hit the ground, this rubber banded segment was released. And so there would be something inside this container that would be held in by these pieces. But once it hit the ground, this would come out, and those pieces would be released onto the ground. And while I was talking about strength of your attachments and building, I wanted to show an example of using these framed pieces as well as the idea of cross beaming to create something that's really sturdy. Now, this was a gear rack for a rack and pinion system that was able to extend all the way across the board. And to do this, it had to be very strong. So you can see that this is a very sturdy attachment that cannot come apart easily. And the way we did this is by using these frame pieces. And then just like the example that we were showing earlier, we put these cross beams across it so that these can't split by pulling. Okay, that's all I had to show. Let's get back to the presentation.
Yep. Here we go. These are just some of the attachments that Arvind was showing. Here's another example of a gravity-based attachment similar to one of the ones Arvind showed. Arvind?
Okay, so we just want to, in conclusion, we wanted to just let you know that you don't have to build something that's complicated, and you can often score more points and be more reliable with something that's simple than something that's complicated. We also wanted to mention that we know that it is tempting to look at experienced teams and want to be like them and want to do what they're doing. And that's also tempting to go online and look at solutions that are out there. And we just want to discourage you from doing that. And that is because one, judges will recognize robots that you've taken from online. And you should also consider that if that design that you're using is even makes sense for the current season. And finally, the team members can often not explain or repair or program something that they did not design. And just know that if you do borrow ideas from another team or another source, you should cite where you got it from.
Next, we're going to talk about programming for reliability.
We do have a few questions, so I think we can answer that since we had some building questions before we move on to programming. Okay, actually this question was about reliable turning. I think we can mention that when in the programming section. So we will get to that.
Does anyone have any questions, or should we move on? Arvind?
I think that was it. And yeah, we'll get to that when we're talking about programming. So, okay, we can go ahead and move on.
Okay. As I was saying, we are going to be talking about programming for reliability. Oftentimes, teams, especially rookie teams, will avoid using sensors because they may seem hard. However, they really increase your reliability. So we highly recommend that all of you use sensors, even if you are a rookie on a rookie team. The first big challenge is navigating to a mission reliably, because LEGO robots are not perfect. Therefore, we recommend that you can use aspects of the mat to make your robot more reliable. For example, you can find lines such as these big, thick black lines. You can follow them to each mission model, such as this one, and go across the board. And then you can align on lines, which means as your robot is approaching a line and your robot is angled, you can then move into the line and then straighten yourself up. You can do a similar technique for aligning on a wall where you back into the wall. We'll be discussing that a little bit more later. And finally, you can use the gyro sensor to help make your turns and moves more reliable. You should use these techniques throughout your runs to make your robot as reliable as it can get.
So let's start by talking about how you can reliably find lines. So a big challenge teams face when finding lines is that there's different backgrounds every year on the first LEGO League mat. And you notice this year has a lot of green on the bottom. And when you're driving over these different colors, it might detect something that is black before it breaches. And it turns out that green actually reads very dark in reflected light mode if you are using reflected light mode to look for the line. So a few things that we suggest are moving for a certain distance before looking for the line, which will ensure that the distance that it's moving for inches before looking for the line, it's not going to stop early there because it's not looking for the line yet. Another thing that we recommend is instead of looking for black, there are some cases where you might actually want to look for the white that surrounds the line. And this is usually in cases where you have something that reads very dark, or if there's black in the background along the way, it might be better to look for white if there's not much white in the background.
In order to reliably follow lines, you have to first get to the line. I recommend using the technique that Arvind just described in the previous slide to find the line. You can either find the white and or the black line, depending on your scenario. And then after you find the line, you have to turn to become straight and parallel to the line. And then you can just line follow. And then we recommend you pick and choose which lines you're going to line follow on. Choose the ones that are most useful, such as those that take you to a mission model, such as this one, or even this one will take you across the entire board. Just keep in mind how you're going to line follow by moving to a line and turning, and which lines you're going to line follow on.
So next, we're going to talk about aligning on lines or squaring up on lines. So what this does is it removes the error in your angle, because it makes sure that your robot is perpendicular to the line and you know what the angle of the line is. And these angle errors add up because when you turn, there's always slight error in how much you turn by a few degrees, and this will fix for that. So the way it's done is it actually uses two color sensors, which is why when I was showing the robots earlier, I made a point that there are two color sensors. And these color sensors are on opposite sides of the robot, which is actually used to straighten up on this line because it makes sure that both color sensors are on the line. And so just a simple way, like explanation of how the code works, it turns on both the motors, and then once it finds the color sensor finds the line on one side, it stops the motor on that side. And so the other one will continue, so it will turn because one is on and one is off. And so it will turn until the other color sensor finds the line, and then it will stop. And your robot should be straight to the line. You can even do it multiple times in a row to make sure that it's perfectly straight.
The next technique we will be talking about is aligning on a wall or a fixed model. To align on a wall, it's actually quite simple. You take your robot and back up onto the wall, and then it will become perpendicular to the wall. In order to do this, you need to do two things. One, you need to have a flat wall, such as an outer wall, as Arvind talked about earlier, on the back or front of your robot. And two, you need to use the move seconds mode of the move block. If you use move degrees or rotations and your robot's wheels stall when backing up into the wall, your robot will just hang there forever. However, move seconds essentially times out. We recommend moving back into the wall for 1 to 2 seconds, depending on how far you are away, and it will time out without getting stalled. You can use the exact same technique to line up on a mission model such as this one. Note that the mission model has to be very firm, because if you align into a mission model that isn't, it will rip up the dual lock, and that is actually on you if the mission model comes out while aligning on it. So you need to be careful which models you align on.
Next, let's look at the concept of wall following. So wall following is another technique that makes sure your robot is straight because you know your robot is going to be parallel to the wall. This can be done using an outer wall, which we described earlier, as well as wheels on the side of the robot, which will make it smooth rolling along the wall. And so you just drive into the wall, and as you drive into it, it will become alongside the wall, one thing that Sanjay and I like to do is put a little bit of a curve on the move, and that will actually make it curve into the wall to make sure that it stays along the wall. And wherever we can, we like to ride along the wall since you know exactly where you are when you're up against the wall and you know that you're straight. Okay, so how can you reliably wall follow? It actually depends. So one problem that people will have when wall following is how to get off the wall when you want to. And it actually depends on which direction the robot is facing, based on what you need to do. So a building solution would actually be to add wheels, as I was mentioning earlier, which will make the connection between the wall and the robot more smooth. You'll be able to curve off the wall. However, a programming solution is to make it curve off very smoothly instead of doing a sharp turn. And the way you actually do this, again, as I was saying, is different based on which direction it's facing. So if you see the figures on the right, if you try in figure 1, if you try and curve off the wall when your wheels are in front and you try and turn to the left away from the wall, the back of the robot will actually hit the wall and get stuck. So in that case, as shown in figure 2, you would actually have to turn right so that the back of the robot goes away from the wall, and that's how you would get off of the wall. And it's the opposite if the robot is facing the other direction.
Next, we recommend using the gyro sensor. One application of using the gyro sensor, other than using it to improve turning, is to use it to keep your robot straight. What you can do is by taking the gyro sensor value, you can make sure your robot stays at angle 0, in essence, just straight. And then what happens is if your robot will hit a mission model or get bumped by something, such as in this green block in this case here, when your robot is all set, it will correct for itself by reading the change in gyro angle.
And
if you are, go ahead.
Okay, I was just going to, while we're on the gyro, I want to just answer the question in chat. We were talking about moving straight here, but you can also use the gyro for turning. And so if you want to make sure that your turns are reliable, using the gyro is one way to do that. You can also look into doing proportional control on your turns, if you're familiar with that. A lot of teams use it for line following. You can also do it with turning to make the robot slow down as it reaches its target so that it is more reliable. Because the slower you turn, the more reliable it will be. Okay, Sanjay.
Yeah. And if you're using the EV3, you will have to use your certain techniques to calibrate your gyro sensor and to accommodate for drift, and also other techniques to accommodate for lag. You can find this on ev3lessons.com. Note that you only have to calibrate your gyro sensor once when the brake turns on. This is not an issue for Spike Prime, but there are other issues with the gyro sensor on the Spike Prime. And creating a gyro move straight program is very similar to creating a line follower because it's the same concept. You're trying to keep an angle at your robot's angle at 0 instead of keeping your robot's color sensor reading at 50. For more information, you can read the gyro sensor lesson on ev3lessons.com.
Next, we're going to talk about the concept of stall detection. So stalling is when you have a motor that gets stuck before it finishes its move. So let's say, for example, a motor arm is trying to move 3 rotations, but it gets stuck on a mission model and doesn't move that 3 rotations. It will keep trying to move that 3 rotations forever, and you will have to grab your robot and lose a precision token. However, if you employ stall detection in your code, it will detect that the motor has gotten stuck and continue on in the code. In EV3, you can do this by monitoring the speed of the motor. So if the motor has dropped in speed or it's not moving, if the speed is 0, then you know that it has stalled. However, in Spike Prime and the Robot Inventor, stall detection is built in, and you can turn it on and off as you need with a built-in block that's shown in the image on the right.
Setting your motors in launch might seem simple, but if you're using something like a menu system, it is actually not as easy as it sounds. When you actually have to reset your motors after you adjust them by hand. The first thing you have to do is set your motors into coast mode, because by default, after you run a move, it will be in brake, so you just cannot move it by hand. After that, you have to reset your motors by doing something, by running this piece of code on the EV3. To put your motors in coast mode, on the EV3, you just change the mode in the stop block and change it to coast. And then you should be able to reset your motor just like that and adjust them in launch. You may be wondering, why do you have to reset it? Let's say you just run putting your motors in coast, you adjust the motor, and then you click play. The moment you move your motor, let's say 20 degrees, it will actually try to undo all the movement that you did in launch, because it keeps track of the encoder and tries to adjust for it. However, resetting your motors will clear that internal counter and will allow you to move it by hand without any repercussions. In the Spike Prime and Robot Inventor kit, you can use a built-in absolute motor encoder to easily reset your motors and launch, because you can always have it move to, let's say, an absolute value of 20 degrees, no matter how you start the arm or whatever attachment it is.
Finally, we recommend that you test your robot often. We have a worksheet that is available at fltutorials.com that's shown at the right, where you can record each test you did and which missions worked and didn't work. And this will help you get an understanding of which missions are more reliable than others. Another thing that you can do to ensure reliability is to test. If you do have more access to more than one table, you can test on different competition tables, since different tables are slightly different. You can also shift the mat and shift the mat to different areas of the board, as well as move the mission model slightly to account for some of the variation that there will be at competition. These are good ways to test if your robot is able to, even with these variations, still work. In conclusion, there are 5 common reliability issues that we discussed. The first is if the robot does not drive straight. The common problems that cause this are the robot being in balance, the wheels not being supported well, or the tire being off the rim. Second is that the robot does not reach the same location each time. We recommend starting at the same area in launch. Align on walls and mission models and lines. Line follow and use aligners, basically all those techniques that we've been talking about. If an attachment doesn't perform consistently, try to build it stronger. Start your attachment motors at the same spot every time. And this is a lot easier actually with the Spike Prime and Robot Inventor because of the built-in encoder or the built-in absolute positioning. And next is if the robot moves an attachment arm, but that attachment arm stalls, then you can use stall detection. And finally, if the robot is crooked after line following, you can align again after the line follower, or you can learn how to do a smoother line follower. Next slide. Okay.
And finally, where you may be wondering, where can you learn more? Everything we have covered, you can find on flltutorials.com. We have some starter robots and lessons specific to Verisego League. All the engineering journal worksheets that we were talking about can be found in the worksheets tab. For programming lessons for the EV3, you can go to ev3lessons.com. For the Spike Prime, primelessons.org. And also for interesting mechanisms with LEGO that you can adapt for use in Verisego League, we recommend looking at the books by Yoshihito Isagawa.
So that's where you can contact us. And now we will answer any questions you have. So
Our first question was, which is more reliable or robust, navigating with the EV3 gyro or the built-in one built into Spike Prime? Well, obviously you cannot use the EV3 gyro with Spike Prime, so
no, he's saying use the EV3 with the EV3, use an EV3 with an EV3 gyro or the Spike Prime's gyro. So I think that both of them have some limitations. So the EV3 gyro had the issues with drift, where your readings would continuously increase if when the gyro was calibrated, it wasn't perfectly still, as well as the problem with lag, where the readings would actually be behind where the robot is. With the Spike Prime and Robot Inventor gyro sensors, this is no longer an issue. However, there are different issues with the gyro sensor and Spike Prime that we have found. One is actually mentioned in chat where the gyro sensor is naturally a few degrees off. And this is hub specific, meaning hub 1 might be 5 degrees off for every 360-degree turn, and hub 2 might be 10 degrees off for 360-degree turn. And this seems pretty consistent. And so I do agree with a solution for that would be to have to naturally, or to it seems like they have just adjusted for it by like subtracting 3 degrees or 9 degrees. And so I think that's a good solution for that. Another thing is that this error increases if you have code that's running simultaneously. For example, if I'm trying to update the LED matrix while I am turning, then that will increase the error to about 20 degrees per 360-degree turn. And it seems more unreliable if you're doing that. So a good thing to do is limit the amount of code that you have running simultaneously while you are using the gyro sensor. So I think that both can be used just as reliably, and they both have their own issues and their own good things about them.
Yeah, I agree with that, Arvind. The next question is, how can we make a line follower smooth? One way to make a line follower smooth is to use proportional control. I'm assuming you're using a basic line follower, just turn left if it's white, turn white, and then turn right if you are on black. That's very jagged, but the way a proportional line follower works is you're looking for how far off the line you are based on your color sensor light reading. And then you are adjusting based on a proportion of that light reading because you want to stay on the edge of the line, which is 50% if you are calibrated. And then based on that error, you adjust your robot accordingly.
So we did have a question on, do you have any lessons on your website on how to square on lines and use alignment? Yes, we do. We have lessons for this for both the EV3 on ev3lessons.com and for the Spike Prime on primelessons.org. So we had a question, is using MyBlocks, if they need to update their degrees in the function for adjusting, will they need to update each program? So the great part about MyBlocks is that you can just change it once and it will change everywhere, which is one reason why we recommend using MyBlocks for things like this. However, for the Spike Prime, since each of your project files, you have to copy and paste the MyBlocks, you will have to change it in each project file. But that should only be like 4 to 6 places at most, depending on how many runs the team has. And also, if you use menu systems or things like that, where everything is all in one program, then you will only need to update it once. Spike also doesn't appear to have total wheel degree feedback. What exactly do you mean by that?
You can set it into two modes. If that is what you are talking about, you can read it as either an absolute position or a relative position based on where you last reset it. The relative position is very similar to how the EV3 encoders work. Yes, you were talking about the absolute position. Yeah, you can set it to the relative position, which will go basically from negative infinity to positive infinity, not just a 0 to 360-degree absolute positioning.
Yeah, so I'm just sharing the code here really quickly. There's the move motors. There's something blocking it here. Can you still see that? Or
Yeah, we can see it.
oh,
That
there we go.
it was actually better before.
Oh, like this?
Yeah, smaller. Yeah.
Okay. And I might actually have to, or you can do position, and that will give you the 0 to 360 degrees.
I think it's
But
negative 180 to 180.
is it?
Is it?
I think it, okay.
Or am I thinking the gyro?
I think that's for the gyro. Oops.
Yeah, I think it's 0 to
But either
360.
way, you get 360 degrees of setting. But you can also do set relative position, and then you can read your relative position. So if you have like a starting point where you can set to 0, then this will keep going up and will give you the degrees counted from your relative position, and this will go beyond 360 degrees.
There's also a question, but how do you control the distance? How could you clarify a little bit on the distance for what? I am assuming that you're talking about using the motor encoders. Using the motor encoders is very important. You can do moving for centimeters. Actually, if you're using the Spike Prime, you can program in centimeters built in. For example, in the Spike Prime, you can say move 7 centimeters, and based on a variable you had preset, it will actually move 7 centimeters. And if you're using the EV3, you can create a my block.
Okay. If you were to go back to FLL today, which programming language would you advise your team to adopt? I'd probably say if we were go back to like our last year first LEGO League, having a lot of experience in programming, we might have tried out the MicroPython in the Scratch programming, or the MicroPython in the Spike programming software, and in Robot Inventor as well. But as if we were like as a younger team, then probably the Scratch programming software.
The Scratch programming software is just as functional as the EV3's, EV3G, that is, or it's now called EV3 Lab. And don't be afraid to go switch to Classroom or even the new Spike Prime because it is Scratch. In fact, those are the officially supported languages now. EV3 Lab is no longer the officially supported one. And it doesn't even run on Mac anymore.
Does anyone have any other questions?
Yes, to get the relative position, you have to import the more motors block in the little plus sign in the bottom left.
Yeah, so I'll share my screen and show what I did again. Now I actually might have to reload.
Just resize your window, Arvind. Resize it. Your Spike window.
Oh, there we go. Okay. So what I did is if you click on the bottom left, where it shows the block and the plus, it shows extensions. This is also true for the Robot Inventor software. And then I've checked off more motors and more movement because those are the ones I use a lot. But there's actually a bunch of other really neat features such as graphing, more sensor data such as RGB readings and acceleration. But I'll show you what I did here. So if you go to more motors, which will show up on the left now since I added it, it will give me the relative position blocks.
I don't think there are any other questions. If you have a question, please ask now.
And if you come up with any questions later, you can always contact us at the contact information that we provided.
I think, Crystal, off to you now.
Yeah, well, thank you guys so much. Yes, if you guys have any other questions for Arvind and Sanjay, you can reach out to them directly. This presentation was recorded and it will be sent out to you guys by Monday. Just allow for a little bit of turnover, and we'll have an FAQ recap as well. It'll be on our YouTube channel, but we'll send you guys the direct link. So you can share that out with your teams. But thank you guys so much. Arvind and Sanjay, can't thank you enough. And I hope you guys
Thanks for having us.
Absolutely. And thank you guys for attending, and we will see you guys soon at another point in time in the season.
Bye, everyone.
Have a great season.
Good luck.